Hello everyone, very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exam, that is BYJU'S exam prep. So guys, very good evening. So this session is related to the practice questions of database management system. Mostly the questions will be from NIELIT examination only. So I have taken all the questions from the past NIELIT question papers. I'll just try to give you a glimpse that what types of questions are asked in the NIELIT exam, so that you can gain some confidence that the question level is very easy. Today we are going to discuss only the questions from the topic normal form and the process of normalization. So let's move ahead. So this is a little bit about myself. My name is Vishal Rawatiya. I have 10 plus years of teaching experience, secured All India rank 393 in GATE 2010. Based on that, joined IIT Delhi for MTech. Afterwards, I have qualified GATE examination multiple times and I have mentored more than 20,000 students till date. Now, below are my areas of expertise. So today we are going to discuss database management system among all those 5 subjects. Now, let's move forward. So guys, there's a special announcement. BYJU'S exam prep team has come up with a very good idea of summer special classes. So during this time, you can utilize your time for the preparation of the GATE exam or NIELIT or ISRO exams, right? So we have already started the classes for electronics and communication in the summer special program. For CSE also we have started the classes in CSE. Satya Narayan sir has already started with C programming. After C programming, I'll start with the database management system, and that will be followed by Murali Krishna sir with theory of computation. So we have already started these sessions. Please join these sessions and get benefited from these sessions. Apart from that, ISRO notification is out. So we are also coming up with the most expected question series for ISRO in electronic and electrical as well as in the computer science branch. So for electronic and electrical, we have already started from the 5th of June, and for computer science, we are coming from the 12th of June onwards. So be ready for that. Now, there is one more important concept. We are coming up with the concept of Trickopedia, in which we will come up with some short tricks using which you can utilize, using which you will be able to save some time during the examination. By the end of this year, that is by the time you will be appearing in the GATE examination, there will be sufficient number of tricks so that you will have a complete encyclopedia type of thing for the tricks. Therefore, we are calling it Trickopedia. And we are going to start this series from 15th of June for EC, electrical as well as for computer science branch. Now, one most important announcement that BYJU'S exam prep is coming up with a scholarship test, national scholarship test, which will be conducted on 11th of June, that is on Sunday at 12 p.m. So do register for this, kindly participate in the test, and you can get up to 90% of discount on all our programs for the GATE exam, right? So and apart from that, I also want to inform you that I'm running a discrete mathematics series on the application. These classes are available for free on the app. So I've already taken 2 classes of discrete mathematics on 6th and 7th June. This series will be for entire month. So during this month, I'll try to complete as many topics as possible of discrete mathematics. Classes will be conducted from Monday to Saturday morning 9 a.m. So if you are not already a subscriber of BYJU'S exam prep app, and if you are interested in learning the discrete mathematics concept, then do register and watch this wonderful series of discrete mathematics. So mind it, these are absolutely free, so you don't need to worry about anything. Okay, so now let's start with the actual session, that is practice questions of database management system, and the concepts are related to normal forms and normalization. So normal forms and normalization are actually applied on the relation, right? So if we look at this, consider a statement in which we have a course. In the bracket, we have defined course ID, section ID, and semesters. Here, the course ID, section ID, and answer will be termed as, what do we call these three things? In a relational algebra, what do we call these things which are written inside the brackets, and what do we call the name of the table? Right? So, very easy question. It has been asked in NIELIT 2021. So, what are the names? And give me your answers. So, what is the answer? So, okay. Let me look at your comments. B. Yes. So, the things which are written inside the bracket are known as attributes or fields of the relation, and this name is known as name of the relation. So, basically, this thing is called relational schema. This is what? This thing is relational schema, which represent the abstract view of a relation. What do you mean by abstract view? What is the name of the relation, and what are the different attributes available in that relation? So, it is known as relational schema. Right? What does it represent? Abstract view. Right? So, in the form of a table, so I don't only want to give you the answers, but I also want to explain you some concepts. So, let's see. If you define a table, in a relational table, here we define the attributes. Let's say if we define the table with a name student, then what informations are needed? You actually need the ID of the student. You need the name of the students. You also want to know the course of that student for which that student has registered. So these are known as attributes or fields of this relation students, right? Now, what does it define? The number of fields or attributes, what do we call them? What is the arity? Have you heard the term arity or degree? What is arity or degree of a table? Arity or degree of a table is nothing but the number of attributes in that relation. Definitely, you will have some entries in this table. You will have some entries in the table. Now, the number of entries or number of rows in the database table will be known as cardinality of that relation. What do we call it? Cardinality. So, just by a simple question, we know so many things. What? So many things, that what is a relational schema? What do we mean by name of the relation? What do I mean by the attributes? What is defined by the number of attributes? What is defined by the number of rows? Each row is also known as tuple. Each row is also known as tuple. Clear? So, this is the basic view of a relational table. I hope everybody understand this, right? Let's move to the next question. An instance of a relational schema. So, I hope you understand the difference between relational instance and a relation. Instance, what do you mean by instance? At particular point of time, the values available in the table is known as instance, because the relational instance after 1 hour may be different from the relational instance of this particular point of time, because after a while you may delete some of the tuples from the relation, or you may add some other tuples in the relation. So, instance is defined for a particular point of time. Clear? So, it is saying an instance of a relational schema R ABC. So, what does it mean? This R is the name of the relation. Again, ABC are the attributes, has distinct values of A. So, for attribute A, all the values are distinct, and the values of A are also allowed to be null. So, it is asking which of the following is true. It is saying A is a candidate key. It is saying A is not a candidate key. It is saying A is a primary key, or both A is a candidate key and a primary key. What should be your answer? Correct Gate easy, correct, Premson. So the idea is, what do I mean by a candidate key? Candidate key is a different definition, but you just need to understand. So tell me one thing. If I tell you that the values of A and B, I'm asking a new question. Just try to understand this. If the values of A and B together are distinct, if the values of A and B together are distinct, then can we guarantee that AB is a candidate key? If values and AB together are distinct, then can we guarantee that AB is a candidate key? Give me the answer. If I say that AB together are distinct, then can we guarantee that AB is a candidate key? So there are two things. One thing is called key, which is almost equivalent to the concept of super key, and another thing is called candidate key. So what is the difference between super key and candidate key? What is the difference between super key and candidate key? So super keys need not be minimal. Super keys need not be minimal, but the candidate keys has to be minimal. Candidate keys has to be minimal. Now, one more thing you must have studied, that a super key with a single attribute is always a candidate key. Super key with a single attribute is always a candidate key. So the moment we know that the values of A are distinct, then we can say A is a super key. Because anything which is having unique value in the table will be a key. Any combination, Pranam Manish, Pranam, any combination which is unique, whose values are unique in the table, will represent a super key. We are not sure whether it is a candidate key or not, but a super key with a single attribute. Do you notice this A is a single attribute? Yes, because this is defined as an attribute of relational schema. So we know that we cannot further divide this attribute A in the subparts. Therefore, A is a single attribute and it is a super key with a single attribute. Therefore, it is guaranteed to be a candidate key. But again, this is okay from the NIELIT point of view. Now you will say, sir, what are you talking about? This is okay. Manish, COA भी continue होगा, धीमे धीमे रुको, है ना? So what am I asking? Yes. From a NIELIT question point of view, okay, that A is a candidate key. A is a candidate key. But tell me, from the GATE point of view, do we have any option as a correct answer in this question? I don't know how many of you are preparing for the GATE exam. But if I ask you that if this is the exact same question, then what is the correct answer if this question is asked in the GATE exam? What should be the correct answer if this question is asked in the GATE exam? If you are preparing for GATE, then you must know the logic. See, this is an instance of a relation. This is an instance of a relation. We cannot define the concept of key based on the instance. We cannot define the concept of the candidate key based on the instance, because instances may change with time. Yes or no? So at this point of time, we may be having the values in the table such that all the values of A are distinct. But after a while, you may see some tuples in which the values of A are being duplicated. Yes or no? So relational instance is not permanent. Relational instance is not permanent. The values of instance may change. Yes? The values of instance may change over the time. Clear? So based on the relational instance, you cannot define the candidate key. Here it is okay. It is a question from NIELIT exam. The difficulty level is not that great. So you can actually say that, okay, you have made a mistake and we understand that this is fine. But if it is a question in GATE examination, then we can actually challenge this question because we cannot define the candidate key based on the instance of a relation. Okay, sir. So this is a candidate key. Now, is it also a primary key? So the moment you are saying that it is a candidate key, option B is ruled out from the correct choices. Now, is A is also a primary key? No. Why? Because primary key are not allowed to take null values. Primary key attributes are not allowed to take null values, but there is no such constraint on the candidate key. There is no such constraint on the candidate key. So A can be a candidate key for sure, but A cannot be a primary key. Clear? So that's the idea. Guys, please give me 1 minute. Okay. Anyway, I'll see to it afterwards. So A cannot be a primary key. Both A is a candidate key. Obviously, it is not correct. So the correct answer will be A. Let's move to the next question. Enough about this. But I only wanted to explain you one thing, that just because we know that the values are unique, we cannot say it is a candidate key, but in this case we can say it is a candidate key because A is a single attribute and any super key with a single attribute will be a candidate key. Okay? But all this definition is being defined based on the instance of the relation. Therefore, logically it's not a correct idea to define the candidate key of a relation based on the instance. Candidate keys should always be defined based on what? Candidate keys should always be defined based on functional dependencies, right? Candidate keys should always be defined based on functional dependencies because functional dependencies are key dependencies. Clear? Correct option may be A. Yeah, fine. Let's move to the third question. Very easy question. Give me the answer. Fatafat. If you are watching this session, then please सबसे पहले तो अगर मजा आ रहा है तो लाइक कर दो. और guys ये सीरीज इस टाइप की आती रहेंगी. I might have started with the very basic questions because this is related to NIELIT exam or ISRO exam, but soon I am going to start the series of database management system on YouTube, in which we will be discussing all the concept of database management system at the inner level, as well as we will be solving the questions of higher difficulty level. So get ready for that. But this is just for revising all the concept of normal forms and normalization, right? So minimum number of super keys in the relation schema R, where X, Y, Z and W are 4 attributes, and we know that X is a key. We know that X is a key. Manish, why 6? Come on. Why 6? Premson, correct answer. So let's see. Let's look at this. Let's assume that if SID, if I define a relation R with certain things, SID, S name, we also know the branch if we know the SID of the student, and let's also define one more thing, father name. So if we know that SID is the key, then we know one thing. What? That the values of SIDs are unique. Values of SIDs are unique. Now, afterward, even if this remaining 3 values are same for all the tuples, then also, so let's see, if S name is A for this, A for this, A for this, and A for this, then also tuple-wise these 2 things are distinct. Tuple-wise these 2 things are distinct. So if tuple-wise these 2 things are distinct, then these 2 together will also form a key. So here SID is a key. This 2 will also form a key. SID and branch name will also form a key. SID and father name will also form a key, because all the combinations are unique. All the combinations are unique. So if SID is a key, so in every super key this SID must be present. In every super key this SID must be present. But out of this remaining 3 attribute, 0 or more number of attributes may be present. 0 or more out of remaining 3. Right? So, in how many ways we can choose 0 or more attributes out of 3 attributes? You can choose 0 or more attributes out of 3 attributes in 2 raised power 3 ways, that is 8. So, there are 8 possible combinations in which S name, branch and F name can be combined along with this SID, and each one of them will represent a super key. Each one of them will represent a super key. So, if X is the key, then this 8 are the different super keys possible. Generic key means super key or candidate key. Again, gate easy CSE. Again, try to understand gate easy CSE. Generally, this key will mean nothing. Let me be honest. If you want to define a candidate key, then you should explicitly say that this is a candidate key. Generally, key can be anything which is having a unique, which is having unique values. Right? But again, the same concept. What you are saying that X is a key, because if you are saying X is a key, then you know that the values of X are unique. Right? And again, X is a single attribute. So even if you call it a super key, it is minimal, because nothing else can be removed from X, because X is minimal. Right? So whether you consider it a super key or candidate key, in both the cases this X will degenerate into candidate key. Yes or no? Gate easy CSE. Got the idea? They do not need to tell you explicitly that X is a candidate key. If X is a single attribute and they are defining it as a key, then a single attribute which is a key is always a candidate key. Clear? A single attribute which is a key is always a candidate key. Right? But still, is this question completely correct? Is this question completely correct to define this B as the final answer? So that's the idea. If you think in terms of, if you think in more detail, then you will eventually understand with X as the only key, it should be writing X as the only candidate key. Why? X is the only candidate key. Clear? Yes. So if you are not saying X is the only candidate key, then perhaps Y or Z or the combination of Y and Z is also a candidate key. In that case, this will also become a super key, because every candidate key is a super key, and any combination, any of attribute combined along with Y and Z will also form a super key. Yes. So we are intelligent enough to understand the thing, but the idea is we are not going to find with the NIELIT authorities to challenge the simple thing. He may say that okay, we are not dealing with the gate aspirant, so you don't need to worry a lot about that. Right? So that's the idea. So maximum number of super keys for the relation R8 is not the right answer. If here it says minimum number of super keys, then right is the answer. Right? Then 8 is the right answer. If it is saying minimum number of super keys, then definitely it is the right answer, because if X is a key, X is a candidate key, then at least 8 super key will be there. If X is a key, then at least 8 super key will be there. Agree or not? Agree or not? If X is a key, if it is guaranteed that X is a key, then there will be at least 8 super key. There will be at least 8 super key, but there may be more than 8 super keys if other attributes also follow the property of a key. Yes. So I am not challenging anything. I have just taken the questions from the NIELIT previous year question papers, and these are the questions from 18, 21 and 22, 19, and there was no paper in 19, but the idea is that I have taken the simple questions from the topic of normal form and normalization. You may find some of the errors, but that's okay. You don't need to worry a lot about that. Okay, so just spare them. But the idea is, for this should be a correct question, this should not be maximum, this should be minimum. Agree? Okay. So let's move. The correct answer is B. For time being, it's okay. Let's move to the question number 4. Give me the answer. Take some time. Comparatively tough question, comparatively, though it is very easy, but still, compared to the last three questions, it requires some understanding of concept of normal forms and normalization. Therefore, I would place it into a easy level question. Previous three were super easy questions. This is a easy question. So what will be the answer? Give me the answer. Fatafat. I'm waiting for your answers. Such questions should not take more than 1 minute. In order to explain it to you, I may take some time, but if you have studied database management system, then you should not take more than 45 seconds. So let's see, to define the highest normal form, what is the first thing which we should understand? The very first thing which we should understand to define the normal form is you should know how to calculate the candidate key of a relation, right? So how do you define the candidate key of a relation? The set of attribute which is minimal and can differentiate all the tuples uniquely is called candidate key, right? But one more thing, if you have studied the concept of candidate key, then you know one thing, what that for a relation, an attribute which is not in the right hand side part, an attribute which is not in the right hand side part of any FD is called essential attribute. Yes, an attribute which is not. So I'm giving you the concept and then I'll explain you the correct answer, right? So essential attribute. So what is an essential attribute which is not in the right hand side part of any FD? So you can actually see that name is present in the right hand side part, roll number is present in the right hand side part, grade is also present in the right hand side part. So name present, roll number present, grade present, but course number is not present in the right hand side part of any FD. Therefore course number is an essential attribute. Means course number must be present in all the candidate keys. So first thing I'll write is the course number, but the essential attribute alone may be the candidate key. So to check whether course number is a candidate key or not, we'll try to identify the closure of this course number. So what do I mean by the course number, closure of an attribute set? Closure of an attribute set defines the set of all attributes which can be determined if you know the value of that attribute. So if you know the value of course number, then what other information can be determined? So look at the right hand, look at the left hand side now. Can course number alone define? Can course number alone can give you the information of any other attribute except itself? No, sir. Course number cannot define any other thing except itself. Therefore, course number is not a candidate key. Clear? It is not a candidate key. So now you will have to think in the form of combination that okay, course number alone cannot define the candidate key. Then perhaps try adding the name. Try adding the name along with this course number and try to find the closure. So this time course number can give you the information of course number, name can give you the information of name, and name and course number together, name and course number together can give you the information of grade. Name and course number together can give you the information of grade. What else is left, sir? Roll number. So if you know about name, you can also tell me about roll number. So you already know about name, therefore you can also tell me about roll number, right? So these two attributes can determine all the attributes. Therefore this is a super key. This is a super key. But is it minimal? So see, let's see. You cannot remove C number from the set of candidate key, course number from the set of candidate key because it is essential. And if you remove name, then this cannot form a candidate key because course number alone is not able to identify any other attribute except itself. Therefore, these two together will form the candidate key. right? So this is one candidate key. Do we have any other candidate key? Now once you have identified one candidate key, you can actually look for the prime attributes. So at this point of time, the prime attributes belonging to any of the candidate key are what? Sir, course number is one of the prime attribute and name is another prime attribute. So let's look at the functional dependencies and check whether any of the prime attribute is appearing in the right hand side of any FD or not. So this is not a prime attribute, grade is not a prime attribute, roll number is not a prime attribute, but at this time of time, name is a prime attribute. So name can be identified by roll number. Therefore, rather than name, you can actually replace it. You can actually replace it by roll number, and this will also produce the same information. So if you say course number plus roll number together define all attributes, then it's good enough. Then it is good enough. But is it also minimal? Yes, sir, because C number cannot go out of candidate key, and if you remove roll number, C number alone cannot determine all the attributes. Therefore, there is also a super key as well as candidate key. Right? So these are the two candidate keys, course number and name. Course number and roll number together will form the candidate keys of the relation. Sir, can we have any other candidate key? So let's look at this. So now there is a new prime attribute, that is roll number. So if you replace roll number by name, then you will again get the same thing. In other two FDs, no prime attribute is appearing on the right hand side. Therefore, we are done. These are the only two candidate keys. These are the only two candidate keys. Now let's look at this. In any FD, if left hand side form is a super key, then that FD is in BCNF form, right? Here also roll number and course number together forms a super key or candidate key. Therefore, this is also in BCNF. Now let's see. So these two are in BCNF, but what is the normal form of these two FDs? Do you see that this RHS part are the prime attributes? RHS part are nothing but the prime attributes. For a relation to be in 2NF, what is necessary? It should be a relation 1NF plus no partial dependency. What is a partial dependency? Partial dependency means proper subset of candidate key determining a non-prime attribute. So there should be, first of all, there should be a non-prime attribute at the right hand side. There is no non-prime attribute. Therefore, none of this two is a partial dependency. So it is actually in 2NF. Now check for 3NF. 3NF says what? So 2NF, actually say 1NF plus no transitive dependency. What is the idea to define transitive dependency? To define transitive dependency, either LHS should be a prime attribute, LHS should be a super key, or RHS should be a prime attribute. If any of these two condition meets, then it is not a transitive dependency. So here Y is a or. Here Y or right hand side part is a prime attribute. Therefore, none of these two dependencies are transitive dependencies. So no partial dependency, no transitive dependency. Then we know that these two FDs are at least in 3NF. Now let's check for BCNF. For BCNF, LHS should be a super key, but in both the FDs, name alone or roll number alone is not a key. That is, LHS is not a super key. Agar super key nahi hai, therefore not in BCNF. If LHS is not a super key, then definitely it cannot be in BCNF. So these two FDs are in 3NF but not in BCNF. These two FDs are in BCNF. What is the normal form of a relation? The least of the normal form of the individual FDs. Will define the normal form of the relation. Therefore, the correct normal form of the relation is 3NF. Clear? Naresh Koshik, you said A. Sorry. Have you got the idea, Naresh, that why it is not in why it is in 3NF? Yes, because there is no transitive dependency. That is, right hand side part is a prime attribute. Therefore, this 2 cannot be transitive dependency. In this 2, LHS is a super key. Therefore, they are definitely in bisecond normal form. Clear? So this is it. So the correct answer is 3. Let's look at this. Question number 5. Give me the answer. Fatafat. Fatafat say give me the answer. Fatafat say give me the answer. Very beautiful concept. If you don't know, then this is a very beautiful concept. Why? Because in a database, the question is asking that in a database there are different attributes. If you actually see at the relational schema, then there will be attribute A, B, C, D, E, F, G, H, I. So this relational schema is actually having the attribute A, B, C, D, E, F, G, H, I. But it is not asking, but the question is not asking for the information about this relational schema, but it is asking for a partition, or it is asking for a subrelation of this relational schema R. It is actually asking for the subrelation of relational schema R. Clear? So we are not worried about the FD sets of this relation, but you should be worried about the FD set of this subrelation, which has only 4 attributes E, D, A, and B. So, to define the normal form, it is asking the relation, this subrelation is in 2NF, 3NF, BCNF, what? So, to define the normal form of any relation, first you need to know what? First you need to know the FD set of that relation. Yes or no? First you need to know the FD set of that relation. So, can you define Ayush? Correct, Ayush. So, I mean, your option is A or your normal form is 1NF. Ayush, option number A is true or normal form 1NF is true. What are you trying to suggest by writing 1? Option number 1 is true or correct normal form is 1NF. Great, Ayush. Right? So, in order to do this, first of all, you need to identify the FD set. Whenever a question asks about the normal form of a subrelation, then first of all, you need to identify the FD set of that subrelation. So, what are the FD sets? So, there are only 4 attributes. So, you need to look for the closure. So, what is E closure? Give me, what is E closure? Sir, E closure will be E. E can determine E. From E, you can determine D. From D, you can again determine E. Can you determine anything else from E? Can you determine anything else from D? E? No, sir. We cannot determine anything else from E. Can we determine anything else from D? So, D can only determine D and E. D can only determine D and E, right? So, in this relation, we will actually say, I am writing the FDs, E can determine D, right? D can determine E. The FDs which are present in this subrelation, I am talking about those FDs. Okay. D can determine E. Now, what can be determined by A? So, this closure will be A to B, B to C, A to B, B to C. A, B, C. You can determine A, B, C, and C does not determine anything else, therefore A, B, C. What is B closure? B closure actually determines BC. B closure actually determines BC. Right? Now, what else you can do? You can actually look at the combination. Can we determine anything new from ED? No, sir. ED is of no use because ED can determine E and D only. Right? Now, look for EA. Look for EA. EA can actually determine E, and from A you can determine B, C. You can E, A, B. But this C is of no use because C is not in the relation. C is not in the relation, therefore C is of no use, right? So from EA you can determine EAB. From EB you can determine what? EAB and D, obviously. Okay, because from E you can determine D as well. From EB you can determine EB. Now from E you can determine D, you can determine B, and no. So okay, so let's look at this. Here you are actually looking at a situation where E determines E and D, D determines D and E. A can actually, A is in the relation, but A can determine only A, B, and B can determine C, but C is not in the relation. C is not in the relation, so we are not worried about that. A, B, C together cannot determine anything else. A, B, C together cannot determine anything else. You can actually say that, sir, F is needed, but F is not in the FD set. Now, B closure will eventually determine B, because B can give you the information of C, but C is of no use, and BC cannot determine anything else. BC cannot determine anything else. So these are the first set of FDs. ED will be of no use. Just 1 minute, because I guess I forgot to plug in the power. Sorry guys, extremely sorry. Okay, so ED together cannot determine anything new. EA will be EA. Let's look at this. EA, so E to D, and because of A you can determine B. So EA can determine EABD. So EA together can determine all the attributes. Do you see this? EA together can determine all the attributes of EA together. If they can determine all the attributes, then it means that EA is actually a super key of this relation. R dash, yes or no? EA is a super key of this subrelation R dash. Give me the answer. EA is a super key of this subrelation R dash because E and A together can determine all the attributes. Right? Now you can actually see that E can be determined by D. E can be determined by D. E can be determined by D. Therefore, DA closure, if you try to calculate DA closure, this will also be DA. Because of D, you will calculate E, and because of A, you will calculate B. Therefore, DA is also a super key. DA is also a super key, and we already know that E alone cannot determine all the attributes. A alone cannot determine all the attributes. D alone cannot determine all the attributes. A alone cannot determine all the attributes. Therefore, these two are the candidate keys as well. These two are the super key as well as candidate key. Right? Apart from that, can you have any other candidate key? Sir, look at this. If these two are the candidate keys, then let's look at the right hand side part. So any other candidate key which we will try to define will be from where? So sir, in this two, E and D, both of them are what? E and D, both of them are what? E, D, A, B. Just 1 minute. E, D, A, B. E, D, A, B. AE and AD, right? AE and AD are the candidate keys. So that's what we know. Now, what are the FDs? Sir, E implies D is an FD. D implies E is also an FD. E implies D is an FD. D implies E is also an FD. So what are the prime attributes? What are the prime attributes, sir? A is a prime attribute, E is a prime attribute, D is a prime attribute. What about B? What about B? Can A determine B? Yes, sir. From here, we know one thing, that A can determine B. Now tell me, what is the normal form of this FD? What is the normal form of this FD when you say A determines B? Sir, this A is a proper subset of a candidate key because this is not a candidate key. EA together forms the candidate key. So it is not a super key. Not a super key. And this B is a non-prime attribute. This B is a non-prime attribute. So this FD is actually what? This FD is actually partial dependency. Right? So if partial dependency exists in a relation, then it is in 1NF, but not in 2NF. If partial dependency exists in a relation, then it is in 1NF, but not in 2NF. Therefore, 2NF is wrong answer because A implies B is an FD which is present in this relation, but that is in 1NF. So 3NF is also wrong, BCNF is also wrong. None of the above is the correct answer because the correct answer for or the correct normal form of the relation will be 1NF. Good enough? Is this okay to everyone? That you do not define the normal form of a subrelation directly from the candidate keys of the original relation. To identify the normal form of a subrelation, first of all, you need to identify the FDs of that subrelation, and based on those FDs, you need to calculate the candidate key, and based on those candidate key, you need to check the FDs. You need to check the normal form. So what is the normal form of this FD? So this is in 3NF because both are prime attribute. This is also in 3NF because both are prime attribute. E implies D is again the same thing. This is again the same thing. This is a non-trivial dependency, but this is the only dependency which is in 1NF, and because of that the normal form is 1NF, not 2NF. Clear? So this is a good question. This is a time-taking question if you are not, if you have not done this type of questions in the past. But if you are preparing for GATE, this is also falls in a category of easy question for you guys. Now let's look at the sixth question. Tell me the answer for the sixth question. Tell me the answer for the sixth question. Identify the true statement. So, true statement from the given statement. So, there are two statements, 1 and 2, and it is asking what are the true statements among these two. So, only 1 is true, only 2 is true, both 1 and 2 are true, or none of them are true. What is the right answer? Give me the answer. If you know, then give me the answer. These are these questions are actually directly from the concept which we study during the GATE preparation. Yeah, correct. GATE's ESE CSE. Right. So what do we know? What is the most adequate form of a relational database table? Most adequate form of a relational database table is a 3NF. Why 3NF? Why 3NF? Because in 3NF you can always ensure lossless as well as dependency preserving decomposition. You can always ensure that you can always ensure up to 3NF that the decomposition is a lossless as well as dependency preserving. Now my question is, if you are giving me the answer, my question is that if we try to decompose our relation into BCNF, then which property may be lost? Maybe, not always, but maybe. Which property may be lost? Which? Lossless or dependency preserving? If you decompose a relation into BCNF, then which of these two properties may be lost? Lossless decomposition property or dependency preserving decomposition property? Which property may be lost? So the idea is the property which may be lost is dependency preserving. What does it mean? You can always decompose a relation up to BCNF. You can always decompose a relation up to BCNF such that lossless join is preserved. We can always decompose a relation up to BCNF such that lossless join is preserved. So the problem is not because of lossless join. Problem is not because of lossless join. The problem is because of dependency, right? That if you decompose a relation up to 3NF, then you can ensure lossless as well as dependency preservation. But if you try to decompose a relation into BCNF, then you may lose some of the dependencies which are present in the original relation. Therefore, 3NF is the most adequate form. So lossless and dependency preserving decomposition in 3NF is always possible. Sahi bol rahe ho. You are right. Now, any relation with two attributes is in BCNF. This is also true. This is also true. If you take a relation R with the two attribute, then what are the possible FDs? So the possible FDs. So you can have the FD set as A implies B. You can have the FD set as B implies A. You can have the FD set as A implies B as well as B implies A. Or you can have an FD set which is empty. You can have an FD set which is empty. So these are the only four possible FD sets for a relation which is having only two attributes. So a relation which is having only two attributes can have only one of this FD set. So this is the FD set, then candidate key is A and this is in BCNF. If this is the FD set, then candidate key is B and this is in BCNF. If this is the FD set, then the candidate key will be A as well as B. A as well as B. So this is the super key, this is the super key, therefore both in BCNF, right? If no, so tell me, what is the normal form of a relation if there is no non-trivial FD? What is the normal form of a relation if there is no non-trivial FD? Forget about a relation with two attributes, right? So the idea is any relation with no non-trivial FD any relation with a no non-trivial FD is always in BCNF. Why? Because loss or because the problem arises because of functional dependency only, right? So problems are present in the relation because of existence of functional dependency. If there is no functional dependency, then what will be the candidate key of that relation? If there is no non-trivial functional dependency, then candidate key of that relation will be composed of all the attributes of that relation together. Okay, all the attributes together of that relation will define the candidate key. So this is also true. So the correct answer is C. Leave it. Correct answer is C. Done. Okay. So this is the last question. This is the last question. Give me the answer so that we are done. Give me the answer for this last question. I don't want to extend this for too longer. And the another idea is that I don't want to overwhelm you only with the answers or the right answers. I also want to give you some concepts along with that if you are preparing for the first time. So otherwise, you know what? There are two categories of the student. One is who already know everything, other who doesn't know anything. So students who already know everything, will waste a lot of time, because they know, oh, these are the easy questions, we already know the answers. And the student, and if I directly give you the answer, the other students who doesn't know anything, if I directly give you the answer, then they will be like, I don't know anything, Baba, what are you doing? We can get the answers from the textbook also. So give us some concept now. So that's the logic. So I will have the combination of both. I'll come up with the questions, but I will try to give you the basic concepts associated with those questions. I may not give you the detail of the complete concept at that point of time, but I would try to give you the basic things which is required to understand the solution of that particular problem. Okay, so what is the normal form? Oh, sorry. Let R ABCD be a relational schema with the following functional dependencies. These are the 4 functional dependencies. This is decomposed into AB, BC, and BD. Now it is asking what is the properties which are preserved, that it gives a lossless join as well as dependency preserving, gives a lossless join but dependency is lost. So let's look at this. So this is the relation. So give me that what are the FDs of this set. Can A determine B? Yes sir, A determine B, therefore A implies B will be a part of this. What will be B closer? Sir, B to C, C to D and D to B. But can B ever determine A? No sir, B cannot determine A, therefore this is the only FD which is present in this relation. So for the second relation, what is B closer? B closer contains C, so B implies C. What is C closer? So C to D and D to B, therefore C can also tell you about B. C can also tell you about B. Now, sir, what about B? Sir, B closer is B closer, B to C and C to D. B to C and D to D, C to D, therefore B to D. What is D closer? Sir, D to B and B to C, therefore D to C is also preserved. D to C is also preserved. So these are 3 relations. R1 is a relation with attributes AB whose candidate key is A. R2 is a relation with attributes BC whose candidate keys are B as well as C, because both of them are keys. Okay. And the last one, R3 is another relation with attributes B and D in which candidate keys are B as well as D. So if you take these 2 relations first, if you take these 2 relations first, then A to B, can we determine B to A? No, A to B. So this is A to B, A to C, and then so if we join these 2 relations, then what are the common attributes? So the common attribute is C. B is common and B closer is a candidate key of R2. Therefore, lossless. These are the concept, right? What? In the relation, if you merge 2 relations, then if the common attributes of those 2 relations is a key of at least one of those 2 relations, then it is lossless. So here the common attribute is B and B closer can determine C as well as D. So here B is the key of both the attributes. If it is a key of any of the relation, then also it will be fine. But here B is the candidate key of R2. So this is lossless. Therefore R2 and R3 can be union and you will get a new relation which will have attributes B, C and D. Now when you combine R2 union R3 with R1, then the intersection or the common attribute is actually B. What is B closer? Sir, B closer actually consists of B to C and B can also determine D, therefore BCD. So B can determine BCD, therefore B is candidate key of what? B is candidate key of R2 union R3, therefore again lossless join, right? Again lossless join. So you can define an order in which if these relations are joined, then at every point of join the relation is lossless. Therefore this decomposition of R into this 3 sub-relation ensures lossless decomposition. Now let's check for dependency preservation. So some of the FDs are directly preserved. A implies B is directly preserved. B implies C is directly preserved. C implies D. We don't know about C implies D yet because C and D are not in the same relation. D implies B. We don't know about D implies B as well. So from this 3, F1 union, F2 union, F3. What is F1 union F2 union F3? F1 union F2 union F3 is this set. Now within this set, what is C closure? What is C closure within this set? So if you determine C closure with respect to this set, then C can determine C. From here, C can determine B, and from here, B can determine D. Therefore, you can actually see that C closure contains D. Therefore, C implies D is preserved. C implies D is preserved. Similarly, you also want to check for D implies B. So this is preserved. May not be directly, but in the union of these three FD sets, may not be directly, but in the union of these three FD sets, the FD is preserved. Next one is, sir, we are worried about D implies B as well. So let's look at the D closure in F1 union F2 union F3. So what is D closure? D closure will be D. Because of D, you can determine C. Because of C, you can determine B. Therefore, D closure contains B. Therefore, D implies B is also preserved. Clear? So you can actually see that all the FDs which were present in the original relation A, B, C, D are also preserved in the union of the FD sets of decomposed relation. Therefore, this decomposition gives a lossless join and is dependency preserving. This gives you lossless join as well as dependency preserving decomposition. Clear enough? So these are the basic concepts. Now, let me tell you one thing. These are very easy questions, and these are all the questions of normal forms and normalization which has been asked in the NIELIT examination since 2018. There will be some other questions from DBMS, but those will be from other topics of database management system. These are the only questions asked in the NIELIT exam from the topics normal form and the process of normalization. So now you can understand the level of the exam will be at such level that you will be easily able to crack the exam if you put on some efforts to understand the concept. Clear? So don't think that why only 7 questions, because the today's session was related to the concept of normal form and normalization related to NIELIT. So I have taken all the questions of normal form and normalization in this session. Tomorrow, I guess tomorrow we'll discuss the questions of relational algebra. Tomorrow, in the tomorrow session at the same time, that is at 9 p.m, I'll discuss the questions of relational algebra. For this particular session of practice questions on normal form and normalization, I am done. Now again, one announcement, as I have told you that I am already taking the classes of discrete mathematics on application, BYJU'S application. Those classes are absolutely free. You can simply register on the application and start watching those classes. So if at all you are interested in watching the discrete mathematics or understand the concepts of discrete mathematics, then you are most welcome. Come and join the session at 9 a.m. in the morning. Clear? So this is it. Thank you very much. If you enjoyed the session, then do hit the like button. If you are new to the channel, then kindly subscribe the channel and press the bell icon so that you can get the notification about upcoming videos of different faculties for different examinations. Thank you guys. See you tomorrow at the same time at 9 p.m. for the practice sessions on the topic of relational algebra, and in the morning I'll be discussing the topic of discrete mathematics. In the topics of discrete mathematics, I'll be discussing different types of relation, and that session will be conducted at 9 a.m. in the morning. Thank you guys. See you tomorrow. Bye bye. Take care.